Hi there, guys. Today we're going to talk really quickly about ratios and how we can interpret them and use them to determine chemical formulas. So you'll want to take notes on page 29 of your ISN as we go through this and pause the video as we work through sample problems to see if you've got the hang of it. So up to this point in Unit 6, we have been talking a lot about ratios, but primarily ratios of substances in a chemical reaction, right? The reactants to products, for example. Well, we also see ratios at another level in a chemical reaction, and that is in the formula of the specific substance. And the formulas of each of the substance give us the relative numbers of atoms or moles, and that's kind of how we're going to interpret them, of each element in that substance. And it's also always a whole number ratio. Okay, so just like we can interpret the coefficients in a chemical reaction to mean different things like molecules, formula units, we can interpret the subscripts in a chemical formula to mean different things. So for example, if we're talking about the molecule NO2, so nitrogen dioxide, if we have one of those units, we can interpret that unit to be a molecule because it's a covalent compound. And in that case, if we're saying we have a molecule of NO2, then the subscripts are going to represent individual atoms, right? So we have 2 oxygen atoms for every 1 nitrogen atom. Now, if we're interpreting our quantity of that substance in terms of moles, which is normally what we do, right? We don't normally deal with just one tiny, tiny molecule in the real world. So if we interpret the amount in terms of having a mole of NO2, then it's important to realize that these subscripts actually represent moles of atoms. So if I have a mole of nitrogen dioxide, then I have 2 moles of oxygen atoms for every 1 mole of nitrogen atoms. Okay, so now being able to think about these subscripts in terms of moles, this allows us to determine a formula for a compound. Because if we can figure out moles of each element, then we can determine the ratio, okay? So there are 2 types of chemical formulas that you'll need to be able to identify, and then we're going to talk about how to calculate the first one here. So the 2 types of formulas are an empirical formula and a molecular formula. So an empirical formula is the formula of a compound that is in the smallest whole number ratio of atoms present. Okay, so you look at the formula, you look at the subscripts, and the subscripts are in the smallest whole number ratio. So for example, sodium chloride, NaCl. We have sodium to chlorine in a 1-to-1 ratio. Another example would be nitrogen monoxide. So again, nitrogen to oxygen, this time in a 1-to-1 ratio. So any formula where the subscripts are in the smallest whole number ratio, we would call that an empirical formula. And it's important to note that every ionic compound formula that we've been writing, remember we always reduced the subscripts. So ionic compounds are always written as an empirical formula, okay? Molecular compounds, on the other hand, so compounds held together by covalent bonds, they might not be in the smallest whole number ratio, okay? So we say that we have a molecular formula. So a molecular formula is a formula of a compound that states the actual number of each type of atom in that compound, okay, as opposed to it being reduced to the smallest whole number ratio. So for example, into O4, so dinitrogen tetraoxide. This would be a molecular formula because the ratio of nitrogen to oxygen is in a 2-to-4 ratio, which could be reduced, so it's not the smallest whole number, okay? So you guys need to be able to differentiate between an empirical and a molecular formula. So I've got a quick check for understanding. So I'm going to give you guys Couple of substances. So here's a couple of chemical formulas, and I'd like you to pause and consider which of these is not an empirical formula. Okay, so hopefully you've considered and you came up with N2O4, which happens to be the example that I just gave. But dinitrogen tetraoxide is a molecular formula, right? Because the ratio of atoms is 2 to 4, which is not the smallest whole number ratio, so it's a molecular formula. Iron oxide, iron 3 oxide, the iron to hydroxide is in a 1 to 3 ratio, so that's the smallest whole number. Sodium sulfate, we've got sodium to sulfate in a 2 to 1 ratio, so that's the lowest whole number. And then tin phosphate is in a 3 to 2 ratio. So all of the other ones are empirical formulas. Okay, so we want you to be able to recognize whether or not a formula is empirical or molecular. We also want you to be able to calculate an empirical formula for a compound. So I'm going to head to the kind of steps to do that real quick. So if you'll write these down in your ISN. So in order to calculate an empirical formula, the first thing you need to do is figure out the mass of each element in grams that you have. Okay, so that's step one. Determine the mass in grams of each element present. The next step is going to be to convert those grams to moles, right? Because remember, the subscripts can represent moles. So you're going to convert the grams of each element that you have to moles. Remember, to do that, you're going to divide by the molar mass. Okay, so that's step two. So after step two, you will have a quantity of moles of each element in the compound, and then you're simply going to pick the smallest quantity, okay, so the smallest number of moles that you obtained in step two, and divide all the other quantities of moles by that smaller number. And what that should get you is the smallest whole number ratio. In other words, it's going to tell you what the subscripts are for that compound, okay? And then you'll be able to write the formula if you have the subscripts. Now, a quick note, sometimes in step three, you don't get nice whole numbers, okay? You might get like 1.5 or something. So if that happens, you need to multiply through by the smallest number that will give you a whole number. So for example, if I got 1.5 after step number 3, I might multiply through by 2 so that I could get the whole number 3. Okay, so those are the steps. Go ahead and pause and make sure you've gotten them all written down, and then let's do a couple of examples. Okay, so here's our first example. It says we have a sample of a brown gas, which is a major air pollutant, and it's found to contain 2.34 grams of nitrogen and 5.34 grams of oxygen. We want to determine the empirical formula for this substance. So look back in your notes. What is step one? Step one is to determine the amount in grams of each element in the compound, and we were given that in the problem, right? So we have 2.34 grams of nitrogen, 5.34 grams of oxygen. Step number two is to convert our mass of each element to moles. So we're going to simply divide by the molar mass of each element. So for nitrogen, that means taking 2.34 grams, dividing by the molar mass of nitrogen, which is 14.01, and we come up with a value of 0.167 moles. So we're going to do the same thing for oxygen. Take the mass that we started with, divide by its molar mass, and we end up with 0.334 moles, okay? So step three, pick the smallest value, okay? So which one of these numbers is smaller? It's 0.167, right? And then divide each of your quantity of moles by that smaller number, okay? So for nitrogen, 0.167 divided by 0.167 gives us 1. For oxygen, 0.334 divided by 0.167 gives us 2. And these are nice whole numbers, okay? So we don't need to do anything else. We have whole numbers. These whole numbers right here, the 1 and the 2, represent our subscript. So we come up with an empirical formula of NO2, nitrogen dioxide, right? So the 1 is our subscript here, which we don't write, and the 2 is our subscript here, okay? So now let's have you try one on your own. So I'm going to read through the problem. I want you to pause the video and try to work it out on your own. So it says, in a lab experiment, it was observed that 0.6884 grams of lead combines with 0.2356 grams of chlorine to form a binary compound. Calculate the empirical formula. So go ahead and pause, follow your steps, try to calculate the empirical formula. When you're done, push play again. We'll go over the answer. Okay, so the answer is PbCl2. So let's look at the work that got you that. So again, step 1, make sure you've got grams of each element. That was given in the problem, right? Step 2, you're going to determine moles of each of the elements. So divide by the molar mass. So lead's molar mass is 207.2. And you come up with this value for the number of moles of lead. Then find the moles of chlorine. So take the grams that you were given in the problem, divide by the molar mass, and here's the number that you come up with. Choose the smaller of the two numbers, so in this case it's moles of lead, and then divide both values by that smaller number. So when you do that, okay, for lead, you come up with a nice whole number of 1, and for chlorine, 2. Okay, so that means the subscript for lead in the empirical formula is 1, so just Pb. The subscript for chlorine is 2, so PbCl2, lead 2 chloride, is the empirical formula for our compound. So there's one additional type of problem that you might get, and it's not too much different, but it's a little different. So here's an example. We'll talk about how it's different and what you're going to do. So in this example, it says a substance has the following composition by mass. It's 60.8% sodium, 28.6% boron, and 10.6% hydrogen. Okay, so when you are given the percent by mass, percent composition of a substance, what I want you to do is assume that the sample size is 100 grams. So what's 60.8% of 100 grams? It's 60.8 grams. What's 28.6% of 100 grams? 28.6. So if you're given a percentage, just assume that it's out of 100 grams. So really your percentage is equal to your number of grams. So for this problem, we would have 60.8 grams of sodium, 28.6 grams of boron, and 10.6 grams of hydrogen. So now it's just like the other problems. We are starting with a mass. So I want you to go ahead and pause the video and try to figure out what is the empirical formula of this substance. That's 60.8 grams of sodium, 28.6 grams of boron, and 10.6 grams of hydrogen. When you're done, come back and we'll work through the answer. All right, welcome back. So the first thing that we did was we figured out how many grams we had of each element. Next thing we want to do is convert our grams of each element to moles. So remember, how do we do that? We divide by the molar mass. So for sodium, 60.8 grams divided by its molar mass gives us 2.645 moles. For boron, the grams that we started with divided by its molar mass also gives us 2.645. For hydrogen, we get 10.495 moles. Remember, the next step was to choose the smallest value, which is 2.645, and then go ahead and divide by that smallest number to determine the simplest whole number ratio. So we're going to take all our moles that we obtained in step 2, divide by the smallest number. So for sodium, 2.645 divided by 2.645 gives us 1. Boron, the same thing. We get 1. And for hydrogen, when we divide 10.495 divided by 2.645, we get a value very close to 4. I think it was 3.97. So we're going to go ahead and call that 4. So we've got these nice whole numbers. So now we can write our empirical formula. It is NaBH4. Okay? All right, so let Miss Weesey, myself, know if you have any questions, and then go on to work on your homework, which is that handout that you put on page 28 of your ISN. Definitely let me know if you have any questions. Thanks.